Thanks. Hi. Is my voice audible easily to the back as well? Yeah, awesome. So hi, I'm Joanna Bergstrom-Lehtovirta, and I'm going to present a study on mapping on-skin input of skin displays, which I did together with Kasper Hornbæk and Sebastian at the University of Copenhagen. So the forearm can be used as a touch surface for indirect input for external displays. That is kind of as a touch surface for visual output, which is provided elsewhere than directly on the skin. Those external devices, previous work has used smart glasses, mobile phones, smartwatches, or remote or large or desktop displays to display output for inputs on the skin. In this work, we address a problem that such indirect touch surface poses for input. So the input and output need to be mapped somehow. Similar than, for instance, we use mapping functions in mapping touch on a touchpad or mouse input to desktop displays. When using the skin, however, we need to know how users perceive their body in relation to the external display in order to develop such mappings. So, for instance, when developing such mappings, we need to decide how the screen is oriented towards the arm. So simply where, for instance, is the left corner? Is the screen flipped or tilted 90 degrees so that the left corner is here on the elbow, or is it just transited in one or transformed in one dimension so that it's near the wrist? So a simple orientation problem. Another thing we need to decide in mapping input to output are how distances scale across the arm, for instance, if the arm is used for input. Are the similar height on the right edge of the display the same actual absolute distance on the wrist than it is near the elbow? So we set out to investigate how users perceive their arm as an input surface, as an indirect input surface in relation to external displays. Our study consisted of 3 parts. In the first one, we tested 3 different displays, a desktop display, content on a desktop display, a smartwatch, an Apple Watch, and AR headset, Microsoft HoloLens, and how the content from those are mapped on the arm. So the task of the participants in this first part of the study was to map content, which are the dots highlighted red on a display on these 3 displays by tapping the locations they would kind of perceive corresponding those on their arm. The participants were free to orient and scale this content on their arm as they liked. And the purpose of this part of the study with these 3 devices was to allow us to analyze whether the different kind of display types affect mapping, whether they influence the mapping, whether they're different in the mappings, and especially the scale and orientation of those on the arm. The second part of the study, the participants mapped 2 kinds of layouts of content, simply just kind of displayed on a vertical and horizontal orientation on a display. In this part, the participants were instructed to use the entire arm, so that the content was kind of like wrapped around the whole arm. So in here, we, in contrast to the first part of the study, we kind of fixed the orientation and the scale, the outer kind of limits to cover the entire arm. The purpose of this was to allow us to collect touch samples of these mappings across the entire arm because in the first one the participants were free to scale those, and of course that meant that we only were able to collect touch samples on local kind of parts around the arm. So having touch samples across the whole arm, of course, enabled us to interpolate kind of distributions of content on it. In the third part of the study, in addition to tapping input, we had in the previous part kind of discrete mappings. In the third part, the participants performed input as swipes. In this one, we used a similar setting, mapping kind of the other one of the layouts of the previous part of the study. But here we flagged always 2 targets, which the participants then swiped from one to another on the arm. The purpose of this one was to simply just compare how the content was distributed with swipes, whether it differs from discrete input. So that was the purpose of this part, to simply compare discrete and swipes. The data was collected by using OptiTrack motion capture system, as we needed a system that kind of leaves the arm bare. So we didn't want to influence users kind of the mappings they created, their perception of those by providing kind of additional landmarks on the arm with markers. So for tracking touch, we just used 2 marker sets on the kind of near the wrist and at the elbow, and left the whole forearm bare, and then a third marker set on the index fingertip to track touch. But of course, for estimating touches, then only based on these couple of markers, we needed to develop touch recognition of our own. So for that, we used participants' arm measures from the wrist, simply kind of the wrist height and the width, and the circumference of the arm near the elbow, and based on those, modeled a kind of touch surface, a cone-like surface displayed here. So the coordinate system we used was just the x-axis kind of traveled along the midline of the arm, or along the ulnae bone here, and then y-axis kind of wrapped around the arm from that bone. The surface of the arm model was constructed by then interpolating kind of an ellipse shape at the wrist, which is based on those wrist measures, to a circular shape at the elbow, based on the arm circumference. Based on this model, we then estimated touch by projecting basically the tracked finger position to the midline of the arm, and then calculating the touch point based on those. We used a small threshold of just 10 millimeters to register touches. So when the finger kind of traveled under that threshold, and then took off, we just took the nearest distance to the mid line of the arm, basically kind of inside the arm, and registered that as a touch. We then wrapped the arm model open to just a planar XY surface and normalize the touch points on that for the data analysis. So the results I'm going to present next are on such a coordinate system from 0 to 1. So the results from the first part of the study, the 3 display devices, I guess the most interesting finding from this part of the study with the 3 displays was that in almost all cases the participants used the posterior side of the arm for input. So we have seen many related work and also commercial prototypes using the anterior side of the arm, but here almost all participants kind of preferred, or at least mapped, the touch surfaces or the output to a touch input on the posterior side. The other interesting finding was that they used always the same orientation. So the top left corner of the display was kind of near the elbow. So basically they mapped the displays like this, or the content on the displays like this. And also this was kind of interesting that even when the couple of participants who used the anterior side or the 7% of the cases, even they did not kind of held their arm vertically in a sense that there as well the top left corner was always near the elbow. Interestingly, we kind of didn't find any effect of display types or any large effects of display types on how participants mapped those on their arm beyond two kind of common sense ones. So the other one was that the input surface for watch, which you can see here on green, was slightly smaller or kind of further up the forearm. But this, of course, they were wearing the watches, whereas on the two other with two other display devices they were not, and of course that allowed to input targets like nearer the or to map targets nearer the wrist. The other finding here in the smaller picture was that the watch was always mapped next to it, so that's kind of common sense finding as well, that that watch face is on the posterior side and it's mapped next to it. And the so this is a one participant's data on that. The HoloLens and the desktop display were mapped on the anterior side only by two participants, which represent the 7% of those conditions. By further analyzing the mappings from the kind of two content layouts where we fixed the orientation and collected data across the whole forearm, from those we found out that the target grids are quite unevenly scaled on the arm. So, for example, kind of if you consider a 1-by or 1-to-1 mapping and assume evenly distributed rows and targets on the arm, for instance, the bottom left content would be located on the y-axis at 0.875. So our data shows that participant actually mapped that content at a point of corresponding 0.68. So there is basically a 19% mismatch between the participants' mappings in relation to or comparing to 1-to-1 mapping, and this of course corresponds to about 19% mismatch on the display. So when for instance classifying input, if you consider this mismatch, basically that point would be falsely classified to be the third target on that column and the last row instead of the fourth one, because it's nearer to that one in a 1-to-1 mapping. A 1-to-1 mapping also would basically assume no slopes or deviations across the grid lines. So these rows would basically stay at a constant height on a display. So our data also shows deviations in this. So for instance, the position of this third row, it changes over 20% when kind of comparing the location near the elbow to a location near the wrist, or the corresponding left edge of a display device and the right edge of a display device. Yes, excellent. Yeah. So those were our main results, but we also to allow kind of more easy exploration of the models, we offer a interface at GitHub for that. So basically, because we scaled and normalized the data, we allow here inputting actual arm measures and then exploring how those models look like in a kind of arm cone model as well. And it works with OptiTrack too, so it has an interface for that as well. So to quickly summarize the implications, so of course these models have implications to tracking input in practice on ARM. For example, those 20% mismatches and how those influence classification. Our models can inform how users perceive their arms as input surfaces for external displays. And in addition to using the models for interpreting input by mapping those directly on display content, they can also kind of act baselines for developing more complex mappings such as relative mappings. So future work can develop those by also giving feedback on the display. A cursor, for instance, which we here could not use as it would have required assuming and kind of implementing an a priori mapping instead of allowing users to map based on their perceptions. Thank you.
All right, we have time for 1 or 2 questions.
Hi, I'm Vikram Mehta, Open University UK. Thank you for the talk. My question is why you restricted the input surface only to forearm and not the upper arm or the palm, back palm area?
Simply for technical limitations. So it was already this. This actually proved to work quite amazingly well. The cone-like model. So we did not experience any like false positive touches tracked, but of course it then having a bare palm and yet a very like accurate touch locations on those is quite challenging. So yeah, that would be awesome to do next.
Thank you.
All right, I have a question. So first of all, I think this is really insightful and useful, and I think it has a lot of potential, so I'm glad someone did that. But what I was wondering about, because when I did my PhD, we looked a lot at touch input and imaginary interfaces, touch on the body and so on, mapping. And I remember that there was a big impact of any kind of markers that you would put on the body to what people did. So I was wondering if you counterbalance or maybe you sometimes left them off. The OptiTrack markers looked at people's moles or something, which we found back then had a huge effect on how people would map and touch locations in the body.
Yeah, that's a interesting insight. Yeah, I last year actually I presented a paper at SIGCHI on kind of so in that one the participants mapped targets based on basically landmarks, or we inspected the strategies and we recognized exactly the same than you had, that like such landmarks are indeed quite much used. And here, of course, we tried to avoid using any actual additional landmarks, but of course it is possible that the participants have used some landmarks that they already have on their arm.
If you had strapped, like in other words, if you had strapped the watch such that the face would face down on the anterior surface, would you think they would have still chosen the posterior surface?
Yeah, exactly. Yeah, that's unlikely. Yeah.
Okay, one more. Make it quick.
Yeah. Hi, Fabrizio from the Institute of Technology. Thanks again for the talk. It was very interesting. Have you considered handedness of participants? Because I would expect that if somebody was left-handed, they would have mapped the screen space on their forearm in a different way, and how that affected the whole mapping system.
Exactly. That's also likely to use the other arm then. So here we actually recruited only right-handed participants. For technical reasons as well. Yeah.
Okay. Cool.